Okay, thank you very much for a nice introduction. And my name is Satoru NAKATSUJI from the University of Tokyo and also affiliated Johns Hopkins. My talk is going to focus on the Weyl, what we call Weyl antiferromagnet. And the keywords is the correlated material and topology, and also frustrated magnetism based on Kagome and the Spintronics. And we're going to focus more on this Spintronics aspect. Overview is, so we're going to introduce topological Weyl semimetal, and so the related material Luttinger semimetals. And we're going to focus on this manganese compound. And if time permits, I would like to also put emphasis on recent work on the energy harvesting properties based on these Weyl magnets. So first, I would like to thank our collaborators. So at the Tokyo, this is the member of our group. Tomita, and Iklas, and Sakai, and Otsuki are the members. And we also collaborate with SINS group and alternate groups for ARPES and this Spintronics spin Hall effect measurement. In the US, we have collaborated with Joe Orenstein, Bob Chu, and ARPS group for optics measurements, and for theory, Arita-san, who spoke in this morning, and Alan McNaughton group, and Fuachen and Goswami in the US. So what we're trying to find out is to discover some functional antiferromagnets. So this is the conference for antiferromagnetic Spintronics. So everybody knows how these antiferromagnets are very going to be useful because of the balancing small magnetization and maybe a few orders magnitude faster dynamics. And so usually this response is very tiny because of the small magnetization, but if we could actually realize the large response, as you found in ferromagnets, that's going to actually replace various, in the various applications by using the antiferromagnets. So here we would like to show that it's actually realized in the manganese X series materials, and this material provides a large response as you found in a ferromagnet, and this is because of the two aspects. One is this, as we have heard, the multipole component that realized in real space magnetic texture. The other is that's Weyl semimetals, this aspect. So which realize the momentum space. So these combinations is quite important to realize something which have never seen in antiferromagnets until recently. So anomalous Hall effect and Nernst effect, which we already have been nicely introduced in the previous talk, and magnet optical effect. And we also show this spin Hall effect. So So the Weyl magnets, so I think this has already been introduced by other speakers. So this is a topological metal with broken spatial inversion and time process symmetry. And there's the so-called Weyl points, which has a linear displacement excitation. And it's quite robust against symmetry breaking, and because of topologically protected character. So it has magnetic charges. So the either plus or minus, and they actually appear as a pair. So they can be viewed as a source and sink of very curvature of fictitious field that generate a large quantum anomalous Hall effect, or chiral anomaly, etc. And so in this 21st century, everybody knows that the anomalous Hall current is driven not by magnetization, but very curvature. And Hall conductivity can be estimated as this integration of all the very curvature in these occupied bands. But until quite recently, ferromagnet is the only material that actually exhibit anomalous Hall effect. And based on this understanding, it can be interpreted in this way. So actually, many theories has already shown this, that the very curvature is proportional to magnetization. So in order to drive the anomalous Hall current in your system, you need to have a large Weyl curvature, it means a large magnetization. So therefore, you need a ferromagnet. But this theory also tells us it's actually directly driven by, not by magnetization, but Weyl curvature. So therefore, in the absence of magnetization and zero field, you should be able to see a large spin Hall, anomalous Hall effect, for example, in the spin liquids or antiferromagnets. So this has already been predicted by many theorists. And this also motivated us to actually find those anomalous Hall effects in these non-ferromagnets or spin liquids antiferromagnet. And that partially also because of the fact that it might lead us to find new topological phases, such as the Weyl and metals. And the first, the example of such kind has been seen in actually not in antiferromagnet, but in spin liquid. This is the material of what paracolic oxide class, and this actually iridium oxide, so that provide the conduction electrons, comes from 5D bands. And when we cool down the system, this is spin liquid, so this actually measurement at the dilution refrigerator temperature regime below a few Kelvin. And when we cool down the system, we found that the whole conductivity goes up, something you found in a ferromagnet. Nonetheless, magnetization remains either zero or very tiny of the order of a few 0.01 mu b per this magnetic moment. And this is actually what we know as a quantum spin ice state is one kind of a quantum spin liquid. So this can be viewed as a chiral spin liquid. And in fact, we found that this magnetization is just paramagnetic-like. There is no hysteresis. But however, if you take the whole conductivity hysteresis, you see very large large hysteresis. So therefore, it indicates it's a spontaneous Hall effect in spin liquid. So this was quite surprising. At that point, we didn't have any theoretical understanding, such as Weyl metal is not yet predicted yet. So but at that point, we found there has to be a large Weyl curvature in momentum space. And later, so the Weyl metal prediction came, and also some understanding of this material actually was made. And we now know that this is actually a class of Luttinger metal, namely a correlated version of topological insulator or mercury telluride. So this has a mass of 200 times, and it only has a Fermi point. There's no other Fermi surface at the Fermi energy, only just a single point. So this is a gapless semiconductor. And this gaplessness actually shows up, for example, in a large dielectric constant. And this can be viewed as a mother state of the Weyl metal. With the time reversal symmetry, for example, Brayton, it can exhibit a large anomalous Hall effect. So this motivated us to start finding this possible large anomalous Hall effect in antiferromagnet, because antiferromagnet is naturally abundant and also much higher energy scale than spin liquid. So there must be some higher chance to find those. And the material we're going to discuss here is this Kagome metal. And this Kagome type of metal is quite recently very popular among the condensed matter physicists, because it's not only just a geometrically frustrated system, but often this harbor topological electric structure. So this is one of such a material. And as a previous speaker introduced, nail temperature is about 430, and it actually has this Kagome material, Kagome structure, and spins actually has a 120-degree order. And but nonetheless, it actually has a small canted magnetization, and that allows us to actually flip the magnetization. But this is too small to expect any Hall effect. According to this empirical rule, this would only introduce a 10 nano ohm centimeter. But in reality, we found that it actually has a much, few orders of magnitude larger than what you expect based on magnetization. So this actually tells us, literally, there has to be new contribution to this Hall effect. So another way of viewing this is to plot Hall conductivity versus magnetization. You can see generally in the ferromagnet, it is proportionally increases with the magnetization. It's a logarithmic, full logarithmic plot reported in this literature. And if we locate these manganese 3X systems, they are far away from this scaling law. So again, there's something it's unusual going on. And if we ask how large a magnetic field is necessary to for the ordinary Hall effect to reach the anomalous Hall effect, and by using the ordinary Hall quotient of these materials, it turns out that this few hundred Tesla is necessary. So the amount of Bailey curvature in the momentum space is equivalent to the size of this external fields. So we have also succeeded in growing the polycrystalline sample or texture samples, etc., thin films. And this thin film character allows us to enhance the signal of the Hall resistance. So if, for example, if we use something like 100 nanometer, the Hall resistance change can be amount to the order of 1 ohm. So this is a few orders magnitude larger than what is usually used to monitor antiferromagnetic state in thin films. And although I don't have the data, so that we also have seen the Nernst effect, and it produces a similar effect as we're going to show in this next section. So here, this comes to this thermoelectric counterpart of the anomalous Hall effect. So this figure has already been shown, and this is the plot for the various type of ferromagnet for the Nernst effect versus magnetization. Again, a full logarithmic plot, and again, it's actually empirically known that they're proportional to magnetization. But if we locate the manganese 13, according to this empirical rule, you are discouraged to measure any anomalous Nernst effect. But when we measure this, it turns out surprisingly large. And also, at the same time, this Cameron Benius and their colleagues has also discovered the similar large value. And it's equivalent to what has been seen, the maximum size in the ferromagnet. So now it's time to consider why it actually could be so large. And the intrinsic contribution is known to be mostly coming from the transverse thermal conductivity. And although this equation is a little bit complicated, but what actually tells us is that at T equals 0 limit, this quotient, the transverse thermal conductivity, is nothing but the Bailey curvature at a Fermi energy. So this means that there is some other mechanism to enhance Bailey curvature at the Fermi energy than the magnetization. So what is it? So here comes the Weyl metals. So in order to further understand the mechanism, so let us use the simplest toy model. So here, suppose you have only a pair of the Weyl points. So then when you tune the chemical potential near the Fermi energy, or Weyl point, sorry, near the Weyl point, because of this large Bailey curvature near the Weyl point, the anomalous Hall effect peaks. On the other hand, anomalous Nernst effect, which is given by the energy derivative based on the Mott relation, shows that there has to be a sign change and the large enhancement again nearby the Weyl point. And we investigated whether this is the case, and in fact, this Arita-san's calculation indicated it is indeed the case for this material. First of all, this bound calculation suggested the Weyl point nearby the chemical potential at this Fermi energy, and one can also tune the chemical potential by manganese this doping level, and we also systematically tuned the manganese doping level and found that it actually followed the theoretical curve. And this is rather this dramatic change. It's actually become almost half by actually this chemical potential shift is actually made by just a few % manganese doping change. So this is a rather drastic change. And this also tells us that there is a very curvature from the Weyl nodes. And we also confirmed by using RPS measurement that band structure is consistent with the DFT calculation. So another test to verify whether there is any the Weyl fermion near the Fermi energy is to use a Chiral anomaly. This is actually high energy physics concept, which is actually telling us that if you have the two Weyl points, there is because these linear propagating fermions, there is a conservation law for each Weyl fermions. But in reality, when you actually apply a field along the electric field, this actually conservation law breaks down, and there must be a huge drop of the magnetoresistivity or a huge increase of magnetoconductivity. And this has been already seen at various Dirac semimetal or the Weyl semimetals. And this is an example for sodium-3 bismuth. When you apply a field along the electric field, indeed, it's actually show a large enhancement of the magnetoconductance. And when you tilt a little bit, actually, this drops quite dramatically because this condition is no longer holds. So we actually tested this using this manganese-tin about material and found that this is exactly the case in this material again. So when we apply electric field along, magnetic field along the electric field, then positive magnetoconductance, and when they are perpendicular, they are negative. And when you do rotation of the magnetic field from the parallel direction, then it drops quite dramatically. So this is something you don't see in even a ferromagnet, I think, and this has never been seen in magnetic materials, and this is quite dramatic change, and this is fully consistent with what is expected for chiral anomaly. So these indicates that these Weyl nodes indeed is located near the Fermi energy and partially contribute to the whole conductivity. And another interesting point that one can actually change its sign by a few hundred Gauss, indicating that one can actually control the large Berry curvature in this material of the order of a few hundred Tesla by just a few hundred Gauss. So obviously what we have to do as a next step is to use the electrical means to control the configuration of the magnetic Weyl points in the momentum space. So this is a kind of schematic configuration, the Weyl point in the Fermi energy, so in momentum space. So one should be able to, for example, rotate these Weyl points. And if you rotate this Weyl point very much faster way, like a terahertz, then it might emit electrical, this emergent electric field. So maybe you might be able to enjoy emergent electromagnetism. And so that is a future direction. So the third topic I would like to touch is a magneto-optical effect. So before going to the details, I would like to also touch on this magnetic multipole discussion. So this, which has already been introduced by Rita-san's nice talk in this morning. So this actually material is a non-collinear antiferromagnet. So if you take two triangle, which is a bilayer, it looks like this. So there's a total magnetization is 0. Okay, so you don't expect any this Kerr effect, for example. But but it turns out so if you make a collinear version of this thing, they share the same magnetic space group. And this actually has the magnetization. So therefore, if you actually use this language of multipole, then this actually belongs to rank 1, just a simple dipole. And because there is no, so there is an inversion symmetry center in this material, so this rank 2, is missing, is not allowed, and the minimum rank is allowed is a 3, so which is magnetic octupole, and this actually breaks time Brussels symmetry, and so therefore one can actually view this magnetic texture as a ferroic order of this cluster, namely a magnetic octupole. So this actually, so it's basically it's a unit that breaks time Brasser symmetry macroscopically. So that also allows us to observe a dynamic version of anomalous Hall effect, which is Kerr effect and also Faraday effect. And we also have seen recently Faraday effect by using thin film, but now time is so limited. I only show Kerr effect here. And this is this Kerr effect as a function of field. You can see very sharp change. And as a function of field, it changes sign. So the negative and positive field and positive and negative field. So the black one is actually correspond to the negative, sign of the Kerr effect. So as you increase the magnetic field, the domain actually, this black domain actually becomes a dominant and vice versa. So there is clearly a domain wall separating these magnetic octupole domains. This is quite interesting. And another thing is that one should be able to use this Kerr effect as a real-time monitoring of these magnetic domains. And in fact, this one can actually do see such a change of the magnetic domain, domain wall propagation. So another interesting point of this, because this magnetic domain wall is actually edge of this magnetic Weyl semimetal, so there might be some additional electric structure than the domain. Okay, so also I would like to touch on the spin Hall effect, and the spin Hall effect is the obviously is a time Brussels even quantity, as you so spin current is time Brussels even. So the angular momentum is flowing from left to right, and even under the time Brussels operation, it's actually the same. So it's time Brussels even quantity, and this has already been tested in the ferromagnet, where the time Brussels symmetry is obviously broken macroscopically, and spin Hall effect. Its sign doesn't change, although anomalous Nernst effect does change with a magnetization reversal. And in the case of, this is for cobalt, but permalloy, it's also been seen by using non-local the measurement in alternative laboratory. And we also check the spin Hall effect by using spin accumulation, and in the collaboration with Professor Otani's group. They made this type of device. So manganese routine, this is a bulk FIB made device, and they put spin detector permalloy on top, and kappa is this probe. As they observe, they monitor the voltage as a function of the field, or permalloy is the magnetization reversal. And if we see this type of rotation, we would find that spin accumulation on the surface does exist. And in fact, we find the clear hysteresis indicating there is indeed a surface, the spin accumulation. And another interesting point, this, because manganese routine is magnetic, and you can actually rotate a spin texture by using magnetic field. So we actually rotated by 180 degree of this magnetic texture of manganese routine, and did the same measurement and found this signal. So namely, the sign become opposite when we actually made flip the magnetization. So this indicates that spin Hall effect must be time Brussels odd in this case. So its accumulated spin must change its sign. So how do we understand this? This is this analysis made by the Fuachen and Anam-McDonald. They actually come up with this type of linear response theory, accumulated spin as a function of electric field, and they found it's no longer dependent on relaxation time. Therefore, it is similar to intrinsic anomalous Hall effect. And it can also change its sign. So that's we talk about we found several interesting new phenomena in antiferromagnet in these magnetization systems. And if we have another 5 minutes, I don't know whether you have, I have, okay, thanks. Okay, great. So then I can start talking about another topic. So we have been talking about the magnetic Weyl and we think this might also be useful for energy harvesting. And now the IoT era is coming, and the trillion sensors now being distributed. And so this obviously requires maintenance-free power source, so you can only use a battery any longer. And this sensor does not actually require so much energy. So it's just require microwatt to milliwatt range. So to operate of sensors and nodes. So therefore, obviously, this thermoelectric power generation would be a good candidate for a power source. And on the other hand, but the Seebeck effect is known to be the leading the thermoelectric effect, but there has been serious issues, and that's the reason why there's no big market for this effect. One is obviously this effect generate electric voltage parallel to the heat current, and that requires us to actually make this type of these electric generators, which has numbers of pillars and numbers of resistance junctions. That makes very, very complicated and also very, very fragile as over a long time usage. And also it requires a high production cost. And also the material that has been utilized is very toxic, sometimes precious, sometimes brittle. And so there are numbers of issues. And now we look at this, what we have been talking about in this session, Anomalous Nernst effect. And this turned out to be it's quite interesting, really, and maybe useful if the power becomes much larger. Namely, so electric field here or voltage is perpendicular to the heat current direction because of magnetization, and that is quite useful for us to make a very simple this thermoelectric generator, and so that actually suppress a lot of the production cost, and obviously there's a numbers of possible material can be used as the materials. So namely, one can use a naturally abundant, safe materials, but nobody has ever paid attention to anomalous Nernst effect because of the fact that output is too small, right? So here comes the opportunity for this the magnetic Weyl. So as I said, Nernst effect does not require any magnetization. As you can see in this figure. So what does it require? It requires large Berry curvature, right? So what you like to have is a Weyl point near the Fermi energy. And so we try to apply this mechanism to the ordinary ferromagnets to see if one can actually enhance its performance by the designing electrostructure. So we found this cobalt-2 manganese gallium does have the Weyl point near the Fermi energy, and it turns out it does have much larger Nernst effect than ordinary materials, ordinary ferromagnets, and so it's actually one order magnitude higher than the previous reports. So this tells us this is just the beginning of the story, and we hope we should be we can enhance this number much further. And since here is the mechanism why it is so much enhanced. So this material is not simply just the magnetic Weyl semimetal, but actually is located very close to what we is known as a quantum Lifshitz transition, separating type 1 and type 2. So because exactly around this the quantum Lifshitz transition, the band dispersion is very, very flat. So the key here is that you need to enhance the density of state of the band that creates the large Berry curvature. So that has the Weyl point. So this is what actually happening and actually realized in this material. And at the same time, the theorist Palab Goswami actually predicted that if there is such this proximity to this quantum Lifshitz transition, there has to be a logarithmic temperature dependence of transverse thermal electric coefficient. And in fact, the observation does show this logarithmic temperature dependence. And this is another reason why we see a large Nernst effect. So we think the Weyl magnet would become a very useful magnet, useful for energy harvesting. Okay, so now time is probably up. So topology in the momentum space and multiple in the real space spin texture. We need to, design both, and to have a useful topological Weyl magnet, and that's actually let us find new functional antiferromagnet and also new phenomena such as topological Spintronics phenomena, magnetic spin Hall effect. And these materials hopefully useful for non-volatile memory and also energy harvesting. Thank you very much for your attention.
Thank you for the very nice